Okay, solar system and its origin. When I first joined the Astronomical Society, a lot of facts were known about the solar system, and there were some theories floating around as to its origin, but a lot of the facts were wrong, and the theory had a lot to be desired and has since been added in the last 50 plus years since I've been in the Astronomical Society. Any theory in science has to explain the observed facts. I've noticed that a lot of people who are not in science have a mistaken idea about what the word theory means. They think it means some sort of a hunch, like Uncle Elmer has this theory that when it's about to rain, his big toe hurts or something like that. That's what they think a theory is. But actually, in science, a theory is the highest form of knowledge, where we have facts that are observed, laws that are based on the fact, and then a theory that attempts to explain what we see in these various laws. For example, if you're familiar at all with the gas laws, like Boyle's law that relates the pressure and volume of a gas, Charles' law that relates the temperature and volume of a gas, and the various observations of the speeds of molecules, all of these things were combined into the kinetic molecular theory of gases, which explains everything that was observed and is able to make predictions based on that, including some that are non-intuitive. Like, for example, the viscosity of a gas increases with temperature. You wouldn't predict that based on what you know about molasses and motor oil. But for gases, it's the other way around, and the kinetic molecular theory correctly explains that. So the theory is the highest form of knowledge and understanding that we can come to in science. It's not just a hunch or something. You hear people occasionally say, well, that's just a theory. Well, that's like saying that's just perfection. That's as good as we can get. So any theory about the origin of the solar system has to explain all the facts that we see. If there are any discordant points, we either got to reconcile that by remeasuring the data and seeing if we made a mistake there, or modifying the theory, or in extreme cases, giving it up if it just doesn't fit what's observed. Because after all, if you have a conflict between some lovely mental idea and what you can see with your own two eyes, what you see has to win out. So all the planets' orbits lie in practically the same plane, especially now that we don't try to include Pluto in among the planets. We'll see a picture of the solar system in just a moment, but I'm sure you have already. All the orbits lie in the same flat disk. Remember from the April meeting where we talked about the sky and the Earth, the imaginary line around the sky that shows how the sun moves against the background of the stars during the year. That's the ecliptic. By the way, all of these previous lectures are online on our YouTube site, and you can get to that directly through the Astronomical Society website, which in turn is listed in the little blue folder. So if you've missed any of the previous talks, you can catch up by looking at them online. So the ecliptic is the path of the sun around the sky, but since all of the objects in the solar system are practically in that same plane, all of the planets and the moon are always very close to the ecliptic in the sky. So why is that? Well, that's what a theory has to explain. All the planets revolve around the sun in the same direction. If we get up on the top of the solar system and look at the Earth from the North Pole side as it orbits around the sun, it's going around the sun in a counterclockwise direction. All the other planets do too. Now that's a strange, curious circumstance unless we can explain it, and a theory about the origin of the solar system would certainly have to do that. That's why all the planets go around the sun in the same direction. Here's a picture of the solar system showing its planarity, except for Pluto. If you can mentally just sort of rub that out, you can see the whole thing is just a big flat disk. Here's a diagram from a little book I had as a child, and I haven't found a better one yet. This is from the Zim and Baker Stars book, A Golden Nature Guide. and there's a lot of good stuff in that little booklet. It cost $1 when I bought it in 1957. If it's still available, it'd be a lot more than that, but it's worth it. If you know everything in that book, you know a lot of astronomy. But here's a picture showing the Earth orbiting around the Sun, and as it does, the Sun appears to be in the background of these constellations along this blue path, which is the ecliptic. And the 12 constellations along this path are the constellations of the zodiac that you'll recognize all the names of Scorpius, Sagittarius, Taurus, Gemini, all of the ones that you see in the horoscopes. That's where the Sun is. And since there are 12 of them, the Sun appears in just about one constellation per month as the course of the year goes by. So, and keep in mind that this is not just the path of the Sun around the sky, but looking at the previous slide, all the other planets and the Moon are in that same plane within a few degrees. So they're also always found in those constellations. Here's another way of looking at it, and that's a map taken out of Sky and Telescope, where it shows where the Sun, Moon, and planets are for a month. You can see the Sun on the ecliptic, there and there. And this one shows the equator horizontal. This is the celestial equator at 0 degrees right across the middle. So now the ecliptic is inclined to that instead of being flat as it was in the previous picture. And we can see that the Moon, as it goes through its phases, is moving along the ecliptic, a little above it sometimes, a little below it sometimes. And the planets, Venus, Jupiter, Saturn, Mars, Pluto, Mercury, all of those are along the, that same ecliptic path around the sky. The Sun itself rotates counterclockwise on its axis in just under a month. And its equator is close to the plane of the solar system. So it's kind of looking like everything is tied together somehow. All the planets go the same way in the plane of the Sun's equator. On the Sun itself rotates in that direction. And nearly all of the planets, with two exceptions, rotate on their own axes in the same counterclockwise direction. As seen from the Earth, that way is eastward. The Earth rotates towards the eastward, which is why the Sun and stars and everything come up in the eastern part of the sky, move across, set in the west every night. So the rotation of the planets all looks the same except for Venus, which has a slightly backwards or retrograde rotation, and Uranus, which something clearly happened to. It's lying down flat in the plane of its orbit rather than the axis being straight up and down or 23.5 degrees tilted like ours. It's tilted 89 degrees, so it's lying flat in the plane of its orbit. So something must have happened to it, and we'll look at that a little bit later on as well. Most of the moons in the solar system also revolve and rotate in this same counterclockwise direction. The moon, obviously, from one night to the next, moves eastward along the ecliptic. But if you were on other planets like Jupiter, you would see the moons of Jupiter moving eastward along the ecliptic as well. So this is true almost all the way across. Now there are exceptions to this, but the theory explains those well in addition to that. So we'll take a look at the exceptions and not just sweep them under the rug. And here's a very important thing. Most of the orbits of the planets and their moons are nearly circular. You know, we sometimes make too much of the fact that Kepler discovered that the orbits of the planets were actually ellipses, but just at a first glance, they appear practically circular. They're only very slightly, percentage-wise, squashed from a perfect circle. So that is something that many of the early theories had a hard time explaining, but the modern theories that we'll look into explain that pretty well as to why the orbits of the planets and their moons are nearly circular. That was another reason for Pluto being banished, as this orbit was extremely elliptical as well as out of the plane of the solar system. So elliptical, in fact, that sometimes it was closer to the Sun than Neptune. So it was clearly out of place as a planet. Continuing, the sun, moon, and planets are all approximately the same age. Now, we won't go into the ways that we know this right now, but there are several, and we will get into it later on in the short course. But this rules out some of the old early theories, because now we know that they are approximately the same age. And however, the compositions of the different planets are drastically different from each other and from that of the sun. The Earth is not much like Jupiter, is it? If we have some sort of common origin, we have to explain how the Earth got like it did and how Jupiter got like it did, and how neither one of them is particularly like the sun. And all of that has to be explained in the theory. So what we're doing here, while we're setting up the idea that a theory has to explain this, is kind of reviewing some of the important facts about the solar system that we all ought to know anyhow. This is going to be the most superficial covering of the solar system you've probably ever seen. We have 1 or 2 pictures at the most of each one of the objects in it, with just a few little interesting things about it. Here's the sun. When we look at it in hydrogen alpha, that form of visible light that occurs when electrons and hydrogen atoms fall from the 3rd shell to the 2nd shell, that gives off this reddish light. And if we look at that, it gives us a sharp picture of a lot of the features on the sun. And we can see that there are a lot of features on the sun. When you think about it, that's kind of an amazing thing, isn't it? You've got a ball of gas. It should be featureless. It should just be a sphere just sitting there. But what makes it have features? Well, the Earth has features. Jupiter has features. It's due to rotation. And within the sun, when you have all of these charged particles and differential rotation, rotates faster at the equator than at the poles, then you have all kinds of twisting magnetic lines that set up all kinds of force fields, and this is what leads to all of the features on something like the sun, and presumably other stars as well. Other stars have spots that can be detected as well as the sun. The planet Mercury, the closest one to the sun. This is the Mariner image of it taken back in 1965. And that was a revelation, because everybody's saying, well, Mercury looks just like the moon. Well, it's certainly got craters, and it's certainly hot, and on the side that's facing the sun at any particular time. So it's a rocky place, not even as hospitable as Venus, and certainly much less than the Earth. It is a rough place, and as you can see, meteors have really done their job on pockmarking the surface of Mercury. This is not the AT&T symbol, although they have co-opted it. This is the planet Venus, and it's covered worse than the Earth with clouds. But these are not like our clouds that are made of water droplets, not water vapor, by the way. Most people tell you that clouds are water vapor, right? Well, they're not. Water vapor is invisible. These are little droplets to make up clouds. These droplets are of sulfuric acid. And a lot of the atmosphere is carbon dioxide. The rest of it is sulfuric acid, which has a cycle, sort of like the hydrologic cycle on the Earth. Goes up, cools, forms into little droplets, and then you have sulfuric acid rain down on the surface, which is like 600 degrees C on the surface. So although it's a beautiful place as seen from the Earth, I'm sure you've seen it in the West in the last month or so. It's been very prominently placed, moving past Jupiter in the last couple of weeks. It's beautiful in that regard, but you wouldn't want to live there. In fact, you wouldn't even want to visit there. So Venus is sometimes thought of as like the twin sister planet of the Earth, a little bit smaller, a little closer to the sun, but drastically different. And then here's our planet, which the more we think about it, it's really unique among all the planets of the solar system and maybe the universe. It has a primarily liquid surface. Now we'll get into the compositions of the planets in a couple of minutes, but none of the others have liquids. They're either solids or gases. That's because most substances only have a narrow range of temperature possibilities for them to be liquids. Of all of the billions of degrees extremes in the universe, from the billions of degrees at the center of a star to close to absolute zero in interstellar space, there's a 100-degree Celsius range where water is a liquid, and most other substances have a narrower range than that. So there's liquids are extremely rare, and we have the only ones that are in any measurable quantities in the solar system. Okay. Mars, often thought of as the most likely other place in the solar system for life to have developed, but the more we investigate Mars, that's pretty well gone away. One of the big things back in the previous, actually 150 years ago, the Italian astronomer Schiaparelli observed Mars very carefully and thought he observed little lines on the surface, which he called channels. But being Italian, he called them canali, which got mutated into canals, which has an implication of some kind of intelligent origin. So everybody was thinking about Martians and canals and little men from outer space and all of that. But once we sent spacecraft pretty close to Mars, the canali or channels or canals kind of went away. There are some dots that you can connect in your mind, which people tend to do. People like to connect dots into a line. Well, the lines weren't really there. The polar cap is made of carbon dioxide, which migrates kind of from one end to the other as the seasons change. And the green forests and brown deserts are not that at all. It's all iron oxide that as the carbon dioxide passes over them, they switch from hydroxides to carbonates and change their color a little bit. So it's not foliage at all that has the greenish color to it. Jupiter, the biggest planet in the solar system, 11 times the diameter of the Earth, rotates in only 10 hours. We'll see the reason for that later on this evening as well. That causes it to be squashed kind of flat, has a larger diameter through the equator than it does from pole to pole. Depending on where you're sitting, you can see that maybe that it's got an equatorial bulge, as it's called. Mine is not from rotating. The red spot here is sometimes red, sometimes not even there. And it's thought to be some kind of a storm, also caused by the rotation of Jupiter, differential rotation. But here we have different chemicals rubbing together to form these different compounds. Some of these are, these colored compounds are thought to be similar to the azo dyes that are used in coloring clothing. So your shirt is about the same probably material as the red spot, especially when it's in its reddest phase. We have a close-up of Jupiter here, an artist's conception made of pictures that are kind of pasted together. Galileo discovered Jupiter and its moons as being like a miniature solar system. Of course, Jupiter was already known as a planet. That little sidebar here, a lot of times when I'm pointing out Jupiter and Venus to people in the parking lot of a restaurant or something like that, they say, how do you know that? How do you know that's Venus and Jupiter? Kind of accusing you like I'm making up stuff. Well, how do you know that's the moon? So I always have. Well, this is the same thing, just next step higher. So, so that's about what it is, because the ancients knew of those. How else would they have named them and named them after their gods or vice versa and give them such significance if they couldn't see them? But people today will tell you can't see any of the planets without a telescope. Well, you know better than that, I hope. So the four major moons of Jupiter, Io, Europa, Ganymede, and Callisto. I eat green cheese, the mnemonic device for remembering those in order from the surface. They are in the plane pretty much of Jupiter's equator, and it's when Galileo saw them moving around, he had a number of brilliant insights, as well as just keeping track of them, how they moved. He said this is like a solar system because, and this proved that things can go around some object other than the Earth. At that time, the predominant thinking was that everything in the sky went around the Earth. Well, clearly, even if Jupiter went around the Earth, which it doesn't, these little moons went around Jupiter and not around the Earth. So that kind of was the linchpin there that led to all kinds of breakthroughs in our understanding of how the solar system and the universe was put together. Saturn, extremely beautiful planet. Galileo discovered its rings, but his telescope was so poor, if you take your glasses off and squint, you'll kind of see what he saw. He couldn't see the distinct rings like that. He said this planet has ears because it kind of looked like ears sticking out on the side. There was an earlier theory that there used to be a moon here and it blew up and left behind the particles. Well, that kind of thing just doesn't happen. It was almost certainly a ring in the first place that did not condense to form moons, and we'll see how that works after a little bit. But they certainly are beautiful, and we've learned a lot about them. They're extremely thin, only a mile or so thick at the most, including the waviness of it. When they appear edge on to us, they almost entirely disappear, and at those times Saturn just looks like a small version of Jupiter, a little bit yellower, but you don't see the beautiful rings unless they're tilted to where we can get a good view of them. Way thinner than a phonograph record by scale. Does anybody remember phonograph records? Planet Uranus, I've got this tilted to show that it is, its poles are in the plane of its orbit rather than perpendicular to it like the other planets are. And it also has a little thin ring system that was discovered kind of by accident. Astronomers were watching Uranus come and cover up a star, and an occultation as it's called. And shortly before the planet was to cover up the star dimmed down a little and then back up. And then after the occultation was over, it did it again. And the only way to explain that would be a thin system of rings around the planet, which have since been discovered by spacecraft using various lighting tricks and enhancements and things. You can actually see it. This is an actual image. The color is souped up, but those are actual photographs there. Neptune, smaller than Uranus. I guess I should have squashed it down a little in the slide there, but it's got a distinct bluish color. How many of you ever seen it? During the autumn observing sessions, we can see Uranus and Neptune near Pegasus, Pisces, Aquarius fairly easily, and we'll be glad to show it to you later on. Right now it's too close to the sun in the sky to be seen. But it's another one of the big gas giants. The four big ones, Jupiter, Saturn, Uranus, and Neptune, are mostly gaseous with probably some rocky content, maybe even metallic hydrogen at the center. But the part you see is gas, so-called surface. Moving on, something else the theory has to explain. The orbits of comets are not in the same plane as the planets, but are pretty much randomly oriented. They go every which way, kind of like the petals of an artichoke. If you look at a model of all the comets for the last 100 years and their orbits, it kind of reminds you of an artichoke, or me anyway. I think of food analogies a lot. And asteroids and meteoroids, those are also members of the solar system. Kepler proved once and for all that comets were not atmospheric phenomena. He discovered or observed a comet in his younger years and had observers in different parts of Europe look at it at the same time and saw that it was in the same constellation at just about the same spot. So that would rule out it just being a few miles above the surface of the Earth in the atmosphere. So it was definitely shown to be solar system objects, and the asteroids and meteoroids. And usually at a observing session, I spend the first half telling people that comets and meteors are different things, but then when you get down to it, there is a relationship between them, which we will also get into, so they're not totally divorced from each other. Here's a nice picture. I've never seen an honest statement as to whether this is photoshopped or whether it was actually photographed, but it's certainly a lovely thing. This is Comet Hale Bopp. How many of you remember Hale Bopp? Okay. That was one of the most spectacular comets I've ever seen. It wasn't the longest one or the one that was around most, but it was certainly one of the brightest. I remember being at a gas station one night, filling up my car, and I looked up under all these brilliant lights, and here is this comet sitting up there. You know, that's some comet when you can see it from a filling station, and you don't have to go out in the country somewhere and barely see it. Asteroid Belt. Here are the inner planets, and then the outer ones farther out. And we can see here's the orbit of Jupiter, and between Mars and Jupiter is where most of the asteroids are located. Although there are a few rogues that work their way into the inner part of the solar system, and science fiction writers and news media people like to make a lot of that it's just a matter of time. Might be 1 trillion years, but it's just a matter of time before one of them runs into us, and that's the end of the world. So I'm sure we will have figured out some way to do it ourselves before that happens, but there's asteroids in there. Also, if you remember a talk I gave about a year ago on the Lagrangian points, these Trojan asteroids of Jupiter, before and after it in its orbit around the sun, those are little clusters of asteroids as well that have a stable spot to just kind of park themselves. They orbit at the same speed as Jupiter and in the same orbit almost, but never catch up to it, never get ahead. Here's a close-up of an asteroid from the Galileo spacecraft. And you can see that, like practically everything in the solar system that isn't covered with a thick atmosphere or liquids, it's all pockmarked from other stuff running into it. Little meteors of various sizes cause all these craters and pocking, and that's the way it is with everything we've ever looked at. It looks pretty much the same. Okay, now for the various theories to explain all of this. So this is the second half of the talk, is possible explanations. Catastrophe theories. Now, the word catastrophe in its origins just meant something happening that was out of the ordinary, a chance, rare incident. But since most chance, rare incidents are terrible, they soon became sort of implicit in the word that the catastrophe was something bad. So that's not what's meant here. We're going back to the origin of the word that means something occurred, some unusual thing happened. Random capture was one of the earliest theories of the formation of the solar system. And I'm ruling out things about like elephants on the backs of turtles and things like that from the prehistoric people. I'm talking about the earliest scientific theories. Random capture. The sun was already there. The planets drifted in from elsewhere, captured by the sun's gravity, and commenced orbiting around it. It's better than the turtles and the elephants, right? But what I've done in the next slide is to list all 10 things. Were you counting them? We had 10 things that the theory had to explain, and how each one of these early theories matches up. Red means it's in conflict with it, yellow means it doesn't address it, and green means it agrees with it. Well, the random capture theory doesn't look so hot, does it? You can see that why would the orbits of the planets lie on the same plane if they were drifting in from everywhere and going into orbit around the sun? Why would they all come in and go around in the same direction? Why would they all lie practically in the same plane? Why would they be rotating on their axes in the same direction, and so on? This is just not a good explanation for what we see. So we have to be good scientists and rule out a theory that does not explain the observed facts. And this one does not. And also, why don't we just see this continuing to happen? Well, we get a new planet every now and then, it just drifts in from somewhere. It used to happen. Why doesn't it anymore? So that's kind of not part of the things that we have to explain, but it does come to mind. Here's another one, solar eruption. Sun was just sitting there, minding its own business, rotating, and then it sent out a huge plume of hot gases which condensed to form the planets. Okay, getting a little better. We look at the list again, we see that we get some green here. The orbits of the planets would lie in the same plane, wouldn't it? If a big plume of gas shot out and sort of went into orbit around the sun, all the planets condensed out of that, they would be in the same plane. They would be going around the sun in the same direction, and it would probably be in the equatorial plane of the sun. So we're doing pretty good. And it would explain why they're about the same age. But here's where we run into some bad trouble. The orbits of the planets and the moons are nearly circular. If something gets shot out of a star like the sun and goes into orbit around it, it would be highly elliptical. It would look more like the orbit of a comet at best than the nearly circular orbits of the planets. And it wouldn't explain how the sun and each of the planets would differ from each other so much. So it's better than the random capture theory, but doesn't explain everything. And here's another main objection. Do we ever see hot gases getting shot out of the sun? Yes, we do. In fact, I've got some pictures of them. They would just tend to dissipate and not form into planets. Here's some early pictures of solar prominences where we have a pair of sunspots and material gets shot out of the sun, loops out into space, falls back in. No planets forming there. This is one that doesn't have a lot of velocity, and the magnetic fields are able to constrain the charged particles and bring them right back in. So coming out, looping up, coming back in. No planets. Here's an eruptive solar prominence that has enough energy behind it to just send it right on out. And if you watch these happen, you can watch them in real time with the hydrogen alpha filters and see the material coming up out of the surface of the sun. It moves farther away, gets paler, dissipates, and it's gone. Never ever see a planet forming in those. Here's a solar flare, another kind of eruption that someday may wipe out our power grid. Jeremy once gave an excellent talk about what we can look forward to when you run out of other things to worry about. That if you ever see one of these right in the middle of the sun, that means that instead of shooting out to the side like that, it's shooting right at us. And whenever that happens, we're in for something. Luckily, you might see some auroral displays and have some radio communications disruptions, but it could take out our whole power grid for possibly years. So yet we still don't get planets forming when these things shoot up out of the sun. So there's one more. I guess I'm beating a dead horse here, but there are more eruptions coming up out of the sun, and you can almost see that. Suppose this goes into orbit around the sun. It's hot. It's material out of the sun. It's not going to condense into planets. Okay, stellar encounter, very similar to the previous one. But this time, instead of material mysteriously getting shot out of the sun, of a passing star, whatever that is, would come by and pull out part of the sun's material, and then that big loop of stuff would condense to form into planets. It has the same pluses and minuses as the previous one. It explains all of the things being in the same plane and going the same direction, the same age and all of that. But again, the orbits being nearly circular is not explained at all. They would be elliptical. Furthermore, one spot on that ellipse would be on the surface of the sun, wouldn't it? If you fire up a rocket that only has one stage and no directional control, if you can get it to go into orbit around the Earth, it will just come right back to the same place it started from. So anything that either shoots out of the sun or gets pulled out of the sun by a passing star will have one of its points of its orbit being the surface of the sun. And naturally, we don't see that with the planets. Although this time of year, sometimes it kind of feels like it, that we're approaching the surface of the sun. By the way, in July, we are farthest from the sun, so let that be of some comfort to you that it could be worse. Okay, and again, the hot gases would dissipate. Okay, now we move up to just before the American Revolution. We start getting somewhere with the philosopher scientist Immanuel Kant, who had this theory. The sun began to rotate. It was there, it was there first, and it began to rotate so rapidly that its equatorial bulge, like Jupiter has, just spread out into a thin disk out into what became the plane of the solar system, and then would cool down and separate into rings, and the rings would form into planets. Okay, so that pretty well accounts for a lot of the things that we see, such as, got lots of green here. Orbits lying in the same plane, revolving the same direction, same as the equator of the sun, its plane. Moons going the same way, nearly circular. Since we had this disk gradually pushing out as the sun rotated, everything would be circular. Not too bad. The main problem is on the next slide. There are no direct conflicts with the 10 principal points that we had. It doesn't address these, but it does explain those pretty well. 1774. Main objections. Same problem as with the last two. First, why would the sun do this? If it's been there minding its own business for billions of years, why would it suddenly start to grow an equatorial disk that would come out and then form a solar system? That's kind of hard to come up with a good reason for that to happen. And if it did, the gases coming out of the sun would be hot and they would dissipate, just like the solar flare or stellar encounter theory. And it would need an impossibly high angular momentum in order to launch the planets this way. It would have had to have been spinning so fast to send out a solar system-like disk that it would have never been a ball in the first place. It would have been a flat disk from the very beginning. And explaining how this happened is impossibly hard, even though it was up to then the best theory that had been proposed. But then, sometimes if you just look at things from a different perspective, like backwards, then it all makes sense. And Pierre de Laplace did just that. He was at right angles to Kant most of his life anyway. They disagreed about just about everything. But Laplace pointed out all of the flaws in Kant's theory, which was what he liked to do, and then came up with the improvement on it. You know, a few years later, he had time to think about it and work it out. It's just the exact opposite. And this theory is remarkable. It lasted 150 years pretty much unchanged, and since then, it's still the basis for what we think is correct. It's just been refined to explain some things that Laplace didn't go into. That's a remarkable achievement in science, is to come up with a theory that goes from 1796 unchanged to the mid-50s and then modified not real significantly after that. Okay, the primordial solar nebula. Now, when we do an astronomy course that covers everything, one thing leads to another and that leads back to that, and it's kind of a circular process of understanding. You've got to jump in the merry-go-round somewhere. So we have decided to jump in with the solar system and then explain where the material for the solar system came from later on and why there was a primordial solar nebula that was rotating and had turbulence in it. We will get to that. That's not being swept under the rug. It's behind the closed door that we'll open in a couple of months. Anything that rotates has a tendency to flatten out. If you've ever seen a real pizza being made, whirl a ball of dough around and it flattens out and gets thinner. You don't roll it out with a rolling pin. It takes care of that just from the rotational motion. So the primordial solar nebula was rotating. That would contract it, and rotation flattened into a disk. Conservation of angular momentum is a big thing here. You know how that works? You've seen an ice skater or ballerina whirling around, arms extended, pull them in close, spin faster, because the angular momentum at a greater distance has to be the same as at a shorter distance. So when you get to a shorter distance, it has to move faster to maintain that same angular momentum. So if you have a big disk rotating slowly, if it becomes a smaller disk, it rotates fastly. So the contraction, rotation, flattening it. As the disk contracted, parts of it were left behind as rings, a series of rings as it's getting smaller and smaller. And those rings eventually would be what would condense into the planets. But most of the material would wind up in the center and become the sun. So you can see this is the direct opposite of Kant's theory, which had the sun there first, sending out a disk that turned into planets. Laplace had a rotating nebula that contracted. Most of the material wound up in the center to become the sun, leaving behind rings in that same plane that would eventually condense and form the planets around it. So it's made a lot more sense that way. You didn't have to worry about things evaporating because everything was close to absolute zero temperature. You don't have hot gases coming out and then trying to confine them into planets anymore. This is a series of 6 extraordinarily poor drawings that I hope you can use your imaginations to see what I'm trying to get across here. The primordial solar nebula. This is kind of looks like a shoe insert, Dr. Scholl's thing, but it's supposed to be a bunch of gases rotating. Actually, it started out spherical and then kind of flattened out. So there's a step ahead of this. The primordial solar nebula. As it would rotate, it would get thinner, flatter, and gravity would pull material in towards the center. That would make it get smaller, which would make it rotate faster, which in turn would make it get even thinner and flatter. So that process is kind of a running away of the flattening contraction process, rotating and flattening. As the nebula shrank down, most of the material wound up in the center, but leaving behind rings, which would eventually become the planets. And within each ring, then, once you get a slight concentration of material, that has more gravity and attraction than the rest of that ring. So as it moves around, it will just start sweeping up and accreting all of that loose material into itself. And within each ring, the first step is called a planetesimal, which is like the protoplanet, or not even a protoplanet. It's the very beginnings of individual planets starting to form. Then, after a while, most of the material has been gathered up into these planet-like blobs around the sun, and the material in the middle is the protosun. It's starting to get hot, but just from compression. No nuclear reactions yet. Anytime you compress a gas, it gets hot, right? If you ever pumped up a bicycle tire, you notice that happening. You take a large volume of gas, keep all the other variables the same except compress the volume, the temperature will rise. So that was the original source of the sun's heat and light, was just the compression from all of that material in the primordial nebula, which may be 100 astronomical units in diameter, 100 times the size of the Earth's orbit, getting squashed down into less than 1 million miles. And that's enough to make it heat up and start to glow. And then, after the nuclear reactions start, we have a tiny bit about that tonight. Then the thermonuclear fusion starts in the sun, and then the planets start to get changed by the sun. And we'll get into that coming up in just a moment. Okay, how does the Laplace theory explain the facts? Well, I won't go down the list again, but you can see we've got all green except for a couple of things that haven't been addressed yet by that theory. Remember all of this till February when we go over the formation of galaxies, and you'll see this is a tremendous amount in common. This creation seems to have used the same technique for stars, planetary systems, black holes, entire galaxies. The same kind of thing happens over and over, including contraction, leaving behind rings in a disk and things like that. It's certainly not unique to this. And I'll show the last picture, I think will convince you. Okay. 1950, remember this was 1796 for Laplace, lasted all the way to 1950 before any substantial improvements were made. And Gerard Kuiper, another Dutch astronomer, that would be an interesting talk sometime, Mr. Vice President, is to have a talk about all the Dutch astronomers, which I think is about half of them all together. It's a little country being underwater, and the dikes holding the sea back must do something to people's heads that make them think about the rest of the universe and where they might go sometime. I don't know, but tremendous number of Dutch astronomers. Yeah, that's right. Didn't have any yard work to do. Yeah. Okay, here's some refinements. Most of these are actually not refinements. These are about the same as in the Laplace theory, just a little more details. About 100 astronomical units in diameter, 10 billion miles. Remember, astronomical unit, 93 million miles, or about 100 million miles, distance from the Earth to the Sun. So this was very big, bigger than the present solar system. Temperature near absolute zero, no molecular motion, just motion from inertia. Composition, please try to remember this. I'll bring it up as often as I can, but this is a fundamental thing right here, that the solar nebula was 95% hydrogen, 3% helium, and 2% everything else. Behind this screen is a periodic table, and you can see that hydrogen is element number 1, helium is element number 2, and it goes up over 110 on this one, I think. Everything else makes up about 2% of that solar nebula, practically all hydrogen and some helium and traces of other things. Probably at that temperature there were some actual molecules: water, ammonia, methane, carbon dioxide. And everything else is pretty much as described by Laplace. So this is 1950, Kuiper. In 1965, about 15 years later, another Dutch astronomer, Yost de Yanga, developed refinements of Kuiper's theory, which in turn was a refinement of the Laplace theory. Fortunately, de Yanga gave several lectures about this in Pittsburgh. At the same time, I was a graduate student in Pittsburgh, and I attended the lectures and wrote down copious notes of everything that he said as fast as I could. He had this pretty good accent, and he went really fast, but I got as much of it down as I possibly could and checked it with some other friends who were there, and we kind of put our notes together and came up with, I think, an accurate representation of this. A lot of this is the same as Laplace and Kuiper, slowly rotating from its inherent turbulence and angular momentum from the Primordial Nebula. 0 degrees Kelvin, 95 hydrogen, 3 helium, 2 others, probably some molecules. That part's still the same. Here's an edge-on view. He drew this on the board, and it didn't look a lot better than this, so I've stuck with this over the years. Here's the middle where the sun is, and here's the tapering disk out towards the edges, and it's the same on both sides. It isn't chopped off like that. So further gravitational contraction would increase the rate of rotation, making the flattening even more. Most of the material, now this is important, had so little angular momentum that it fell into the center. If you send up a satellite or any sort of a space vehicle straight up over the Earth, and you don't give it a component of motion tangent to the surface of the Earth, but just get it up there like throwing a rock straight up, what will it do? It'll just come straight back down because it doesn't have any angular momentum. You have to kick it with angular momentum to put it into an orbit. And in this primordial nebula, the molecules moving around had the complete spectrum of angular momentum. Some of them had none. They fell into the center and became the protosun and then the sun. The ones with the greatest angular momentum would go into orbit around that ball in the center, separate into rings, and eventually become planets. So it's just a matter of angular momentum as to whether it wound up in the middle or stayed out in the disk. Now, since then, about 1985, the best I can tell, astronomers, astrophysicists realized they had left one important thing out. It's not important today, but it seems to be an important part of the formation of all systems like this. And that is that whenever material falls into the center, whether it's in a solar system forming or a black hole or a galaxy forming, you not only have material falling into the center, but there's a discharge of material at right angles above and below the plane of that disk. So stuff is shot out above and below. Apparently that energy of stuff falling in has to go somewhere, and the likely place for it to go is to be shot out of the center above and below the plane of that disk. So that is added in here, this bipolar outflow. Here's the material in the disk falling into the center, becoming the protosun, while at the same time there's this bipolar outflow above and below the plane of the disk. And we'll see that come up again later in two different places in the short course. Now, this is an artist's conception of what's going on. This is an actual photograph. Here is the edge on. You can see the thickness of the disk, material shooting up and down from it. The reason it's dark around the middle is not because it's two pieces like a hamburger, but because there's dark material obscuring the light from the center. If you could see through it, there'd be a tremendous blinding glow there from the new star forming in the center. But as it is, the disk itself is blocking us from seeing it, kind of the way the dust and gas in the Milky Way keeps us from seeing right into the very center of our galaxy. Same principle involved there. So we've got right in the middle is the protostar, which we can't see, the accretion disk of the material falling into it, and the jets shooting out above and below. And here's the scale, 100 astronomical units, which is bigger than the solar system. So you can see this is a large-scale object. Not compared to a galaxy, but compared to our solar system, it's bigger. Here is the next of de Yanga's drawings, which again, I think I did justice to. We have, after about 100,000 years, most of the material had wound up in the center, but it kept getting smaller because of gravity making it contract. And of course, it was spinning faster and faster. And around it, this again, remember, is a chopped cross-sectional view. We have an inner ring and an outer ring and some stuff in between the two rings. So in your question, it appears that we probably did not have, say, 8 rings forming at once. We had a great big inner ring and a big outer ring with a little bit of debris in between them, and then those rings themselves sort of separated after a while. For again, unknown but very interesting reasons. Remember, in science there's a reason for everything. It's just a lot of times we don't know what it is. So that's what we have to do next. Okay, then that happens. The inner ring separated into 4 little rings. And remember, these are not balls yet. This is the cross section of 8 rings with little things in between. And these would eventually become the protoplanets, which were balls, maybe 1 million years later. Here's an artist's conception of that, with the protosun doing its thing in the middle and the jets coming up and down, which you don't see in the 1965 version or the Laplace or Kuiper versions. but now you do. Material shooting up and down out of the disk, and here's a protoplanet in the foreground, a planetesimal coalescing out of all the little particles that are out in this portion of the disk out near us. Very good drawing. I just wonder how true it is. Now, here we come to what for me is one of the most interesting parts. First, thermonuclear fusion begins in the sun. You can squash that disk down to the ball in the center down to a certain point, and then the repulsion between the protons, remember it's hydrogen, and the protons repel each other. But at high temperatures, the atoms are going very fast. And at those pressures, they're squashed very close together, and that helps them overcome the repulsion between them, and they start to actually fuse together, to merge. And 4 hydrogens convert into 1 helium atom with the release of energy. That is the overall equation for what takes place in the center of the sun and any other star like it, is this thermonuclear fusion. Then, once the sun is doing this, it's putting out that energy in the form of light and heat, and begins to heat the planets, especially the 4 inner ones. And that causes the gas molecules to move faster and faster according to this equation. Now, some people seem to be afraid of equations. Maybe they were bitten by one as a child. But equations are our friend. They're sort of like recipes when you're cooking something. You don't have to figure it out from scratch every time. It's just a little procedure that you plug into, kind of like 2 plus 2, we know what to do. And here's the equation that gives us the average speed of molecules. There are only 2 variables in this equation, the temperature and the molecular weight of the molecule itself. We can see that at a higher temperature, the molecules move faster, okay? At the same temperature, the lighter the molecules are, this is in the denominator, so the smaller that number is, the higher the speed. So if you have a mixture of all different gases at a given temperature, the hydrogen, helium will be moving fastest, right? Those are the 2 smallest elements. The heavier ones will be moving slower. So that's all this equation tells us. Here it is again. And that's what I just said. I was getting ahead of myself, but there it is. The lightest molecules move the fastest. Now, if we increase the temperature, then they all move faster. But still, the hydrogen and helium will go fastest and the others will move the slowest, but faster than they were at the lower temperature. Okay, is everybody clear on that? Okay, here's another equation, escape velocity. I'd never heard of escape velocity till 1957 when we started launching satellites. And then I started getting into it in a big way, and read in an encyclopedia that the escape velocity from the Earth was 7 miles per second. If you could go outdoors and throw a rock up into the air at 7 miles per second, or shoot a rocket up into the sky at 7 miles per second or greater, it would just keep on going. That's the escape velocity from the Earth. The escape velocity has mainly to do with the mass of what you're getting away from, like the Earth, for example. In this equation, m is the mass of the body that's being escaped from, sort of, in that example, it was the Earth. R is the distance from the center, which would be, in the case of the surface of the Earth, like 4,000 miles from the center. If you had a more massive planet of the same size, the escape velocity would be higher, wouldn't it? Because that's in the numerator. If you had the same size, or same mass planet like the Earth, but you squashed it down to half its size somehow, and that number is smaller, then the escape velocity would be greater because you're closer to the center, which is where you can consider that all the mass is at the center. Mathematically, you can do that. So that's the equation for escape velocity. And it doesn't depend at all on the escaping object, whether it's a rock or a rocket. Makes no difference. The escape velocity from the Earth only depends on those 2 properties, the mass of the Earth and how far you are from the center of it. Okay? Now, we put these together. This is where the miracle of the differentiation of the planets in the solar system comes from. After 10 million, 100 million years, protoplanets started heating up from their own contraction and the radiation from the sun and from radioactivity within them, like decaying heavy elements and so on. The lighter molecules would achieve the escape velocity from the small planets and get lost. Okay? Let me just say that again. As the temperature increases, the velocity of all the molecules increases, right? Until the escape velocity is exceeded, and then they just fly on off. What reaches the escape velocity first? The smallest elements, the hydrogen, helium, reach escape velocity first and leave. And which planets does this mainly apply to? The smaller ones that don't have a lot of gravity in the first place, and the hot ones, which are same four, the four inner ones. So, jumping ahead to the present, Mercury has essentially no atmosphere. Venus, all it has left is some heavy molecules like carbon dioxide and sulfuric acid, molecular weight of 44 and 98. Earth has some molecules, little water, little carbon dioxide. Mars has lost most of its atmosphere because even though it's colder, because it's farther from the sun, it's also a lot smaller, so its escape velocity is less than that from the Earth. So cold molecules can still escape from Mars, only leaving the carbon dioxide and a little bit of water behind. The gas giant planets, Jupiter, Saturn, Uranus, and Neptune, especially Jupiter, are pretty much like they started out. They are so massive that their escape velocity is enormous. And they're so cold that the molecules aren't going very fast anyway. So they've kept everything they had from the primordial solar nebula. It's still there. So they've stayed the way they were. And the four inner ones have been distilled out of all of the lighter elements, and all that's left was that 2% other that we started with. Remember the 95% hydrogen, 3% helium? It's gone. The 2% other is all that's around us left. So now, yes, I just said that. 2% other from the nebula of the inner planets. Okay, here's a interesting thing. It kind of makes it look like a cutaway view of the planets, but it's really a pie chart. So, so the Earth, you can see, is mostly rock. That's that 2% other. And a little bit of ice. And ice, by the way, doesn't necessarily mean H2O, but any sort of frozen gases that are out of their liquid or gaseous state, but solid. So those are solids. And then gases, it doesn't even show up on the Earth. Our atmosphere, as important as it is to us, doesn't even show up on the pie chart. Move out to Jupiter, we see the opposite thing. It's almost all gas with some rock, which may or may not be like the rocks on the Earth, but I'm sure there's some of that material in there. And ices, which can be frozen methane and ammonia, not necessarily like snowflakes or anything. So don't get the wrong idea about what Jupiter is like. Saturn and Uranus and Neptune are about the same, but the proportions are different because they're smaller. Even though they're colder, they've lost more of their gases and have a greater percentage of the rock and ices in their composition. Okay, is everybody clear on how that works? Okay, here's some miscellaneous things to finish up with. The large moons of the outer planets are formed by the same way as the planets themselves, like the four Galilean moons of Jupiter probably were rings around Jupiter, just as Jupiter itself was a ring around the sun. There were these four rings around Jupiter, each one of which condensed into Io, Europa, Ganymede, and Callisto. When I first got interested in astronomy, it was a big thing to remember how many moons each planet had. And they would keep discovering more and more and more. These are tiny little chips. They get a bigger telescope, they'd find another little chip in orbit that might be at a catawampus angle and going backwards. They're not moons. Those are little captured asteroids or something. Jupiter has 4 moons, so take it from that. Jupiter's got 4 moons and you can see them through a small telescope. And it's got a couple of dozen chips that also float around it. Some of the rings, if they were too close to the planet, the tidal forces would keep them from separating into or condensing into moons. If a ring is too close to its planet, the inner edge is significantly closer to the planet than the outer edge, and that keeps it stirred up and it can't condense down into a planet but stays, or a moon, but stays as a ring. And Saturn and Uranus, and actually Jupiter turned out to have a little thin ring system as well. The outer moons of Jupiter almost certainly captured asteroids. They're about half and half in and out of the plane of the solar system, and about half of them revolve around Jupiter in a backwards direction. Kind of like the random capture theory, but from a plane, right? They're very elliptical orbits, some of them this way, some of them that way, because they were randomly captured. So the outer moons of Jupiter are like the bad theory of the solar system. The outer planets have free rotation, meaning they're not mechanically linked mathematically to anything else. Jupiter, for example, rotates in about 10 hours, and we know the Earth's 24, Mars is what, 23, something like that. So the planets have their own rotation periods that are separate from everything else, because they weren't tidally locked to the sun. As big as Jupiter is, its inner edge is not appreciably closer to the sun than its outer edge, is it? It's, you know, several hundred million miles away, so even though it's big, it doesn't get tides on it caused by the sun. Even the Earth, at our distance, is freewheeling. We have our 24-hour rotation, and the most the sun does is collaborate with the moon to raise several feet of water up and down. That's all the tidal effect we have. It doesn't stop the rotation. But for Mercury and Venus, they were so close to the sun that their inner and outer edges were significantly different gravity attraction to the sun than each other. So the inner edge is getting pulled harder. What you got to do is get like one big mountain over on that side and it stays put. Like the moon with the Earth. You have the same side of the moon facing the Earth all the time because it's so close to us that the inner and outer edges have a different pull from the Earth. And those inner planets have a different pull from the sun and got locked in. Now, Venus kept getting smaller and smaller, and when it did, the conservation of angular momentum gave it an extra pull to break free from that tidal locking. I could picture it kind of rocking back and forth like the moon does with the libration. Sometimes it's a little ahead, sometimes a little behind, as Bill talked about last time. And when Venus broke away from that tidal locking, it happened to be when it was going backwards. So it has about a 600-day rotation period in the clockwise direction, which is opposite from the way all the other planets do. Mercury is even stranger, and I've got a picture of that coming up. In fact, there it is. Mercury has a 1 to 2? That should be 3 to 2. This is not my most recent version. I've changed that since then. Anyway, that should say 3 to 2. Suppose we start right here. Mercury's got this side facing the sun. As it goes around, it's rotating in the same counterclockwise direction. By the time it gets back to where it started, that side is facing back out again. You notice it's made 1.5 turns, right? Here to there is a whole turn, and then back out to here is a half a turn. So the wrong side is aimed back out. So we have 1.5 rotations in one revolution. So that's 3 rotations in 2 revolutions. So this should say 3 to 2 synchronous rotation in that picture. When I got first started in astronomy, I keep saying this thing, things have changed, and you'll be telling your grandkids that someday. They said that the same side of Mercury always faced the sun. That was in all of the big astronomy textbooks. Same side of Mercury always faces the sun, just like the moon and the Earth. What happens is we took the data incorrectly. As it works out, every other time Mercury is at a convenient place to see, and it's never really convenient. I believe it was Copernicus or Tycho, one of them never saw it. And it's so difficult because it's so close to the sun, you have to get up on a hill with a flat horizon in the twilight and see it. And even with the biggest telescopes, it's still murky, and you can hardly see any details on it. And you have to wait till the ecliptic is almost straight up from the horizon, so that when it's at its greatest distance from the sun, most of that distance is above the horizon. If the ecliptic is kind of low to the horizon, then even if it's far from the sun, it's not far from the horizon, so you don't see it. So what they did was they would always observe Mercury every other time. And you can see what that did. If you observe it every other time, it's back to the way it was again. So if you observe it every 2 revolutions, you do see the same side every time, and you get the idea that it keeps the same side towards the sun. If there had been large southern observatories back in the 50s, then they would have discovered that, because they'd be looking at their optimum times would be the times that ours weren't. So that wouldn't have happened, except all the big observatories were in the northern hemisphere, and we took the easy way out by looking at it every other time. So that's a little interesting fact, I think, about Mercury. Okay, Earth-Moon system, a double planet. The ring that condensed to form the Earth condensed asymmetrically with a big part and a little part. One was the Earth, one was the Moon. You see all kinds of fanciful things every now and then online about how some passing planet ripped a chunk out of the Pacific Ocean and that became the Moon. That's got everything wrong with it that our careful examination of the random capture or passing star theories were wrong about the solar system as a whole. So I think you can rule those out. Comets. Now, when the Primordial Nebula condensed to form the flat disk that became the sun and planets, it was spherical. And way out there beyond the fringes of the solar system is a spherical cloud of debris that was left over from the formation of the solar system. That's known as the Oort cloud, after yet another still further additional Dutch astronomer, Jan Oort. And he hypothesized, and it's since been just about proven, that there's this cloud out there that's the source of comets. And occasionally material, gravitational forces add up to bring a piece of that material in. From there, it falls into the inner part of the solar system, gets near the sun, blossoms into a comet, goes back out into the far reaches again. Comet orbits are, like I said right at the beginning, all different directions. They're not in the plane of the solar system. It's exactly like you'd predict from the random capture theory, because it is. The spherical cloud of comet nuclei in the Oort cloud falls into the solar system randomly from different planes, different directions, so the comet orbits are randomly oriented like we would expect from random capture. Some meteoroids, like the big ones that form Meteor Crater in Arizona, are probably escaped asteroids. And very small ones that were comets and break up into little pieces and smaller pieces. Remember, a comet is like a dirty snowball. We'll get into that more later. After several trips around the sun, all of the snow is gone and all that's left is the dirt. So all the little pieces are there, and when the Earth plows through them every year in its orbit, then we have a little meteor shower. So these are like little grains of sand. The whole Perseid meteor shower coming up next month that you can see spectacular meteors, every couple every minute. You'll see those are just little grains of sand burning up about 50 miles in the air, and those are from burnt out comets. Okay, here's the true test of a theory, and that is it can predict things that you don't already expect. And the de Yanga Kuiper-Laplace theory predicts that if this happened once here, it could happen elsewhere. And so astronomers have been looking for the signs of other solar systems. They can form if the angular momentum is right. If a primordial nebula has no angular momentum whatsoever, which is unlikely, as we'll see later on in the beginning of the universe, then all the material in it would just fall into the middle and you'd have a single star. It used to be thought that that was usually the case. When I was getting started, they said maybe as many as a third of all stars are double or multiple. Now it's probably more like 80%, and the rest of them probably are planetary systems. It's hard to find a single solitary star anymore. If there's a lot of turbulence and it's all stirred up, then the nebula subdivides into big pieces and forms a multiple star system, like Castor, for example, has got 6 stars in it. But like Goldilocks, if it's just right, not too little, not too much, it will have some angular momentum. So most of the material falls into the center and becomes a star. The rest of it flattens into a disk and then rings and becomes planets around that. I remember when they first decided that the Orion Nebula was the birthplace of stars, especially the trapezium region right there at the tip of that little finger sticking in. Here's a close-up of the trapezium 4 stars from the Hubble telescope, and you can see little things in here look like they're flying around. These are new stars being formed with their accretion disks around them, but the pressure of the light and heat from these stars is so much it's blowing it out behind them, kind of like a comet. Most of them don't make it. A lot of these are just evaporated by their surroundings and don't make it. They need kind of a quiet place to settle down, not too close to any other stars, so that they can settle down and without all of their outer vapors and everything being blown away and dissipated. Here's one of the ugliest words, proplids, almost as bad as quasars. Proplids are protoplanetary disks in the trapezium region. Here's a nice one up here that we can see dark with a little star in the middle of it. We're probably kind of looking down on top of it. And here's some edge-on ones again with that teardrop shape because there's a star up here blowing the material away from it. Here's several others. And boy, I hope the next one is what I think it is. Here's a particularly nice one, edge-on with a star glowing in the middle. This is probably going to be solar system someday. Here's its heat and light is counteracting it's kind of a shock front here from the heat and light from some other star, but it may make it. It's heavy enough to do that. Just look through these, you'll see that happening. The picture from this year that shows the ALMA, the sub-millimeter array of telescopes in Chile, it showed exactly like the drawings and pictures that we've had before, a new star being formed in Taurus, HL Tauri, that had the rings after it. This telescope is 66 telescopes. Some of them are 40 feet in diameter, some of them are 20 feet, and it's spread out over a range of 10 miles. So it's got a tremendous resolving power. And there's none of this little fuzzy stuff like we were just looking at. It looks like another whole solar system forming, but it's not an artist's conception. It's a photograph from the ALMA telescope. So I'll lay off here. We'll have about a 10-minute break, and then Tom will tell us about the optics and telescopes for the second part of the program. Thank you.